Hey, welcome back. Today we're going to break something you probably thought was solved. RAG. Retrieval Augmented Generation, RAG, was the breakthrough that made everyone think we'd fixed hallucinations forever. Embed your docs, search by similarity, inject into the prompt, done. And for simple use cases, it works great. But here's the thing. The questions that matter in production aren't simple. They require connecting dots across documents, tracing relationships, understanding what happened when. Basic RAG can't do that. And if you've ever wondered why your RAG system feels shallow, this video explains why and what to build instead. Augmented generation was revolutionary in 2023. RAG felt like magic until it wasn't. Here's the question that breaks basic RAG. How does the delay in Project Apollo impact the Q3 budget that Sarah approved? This requires multi-hop reasoning, connecting Project Apollo to its dependencies, those dependencies to budget items, and those budget items to Sarah's approvals. Vector similarity search returns documents about Project Apollo and documents about budgets, but it can't traverse the relationships between them. Or consider this. What troubleshooting steps worked for similar issues last month? Basic RAG finds similar issues, but it doesn't track what happened when, whether the solutions worked, or how the context of those past interactions relates to now. RAG was table stakes in 2023. By 2026, it's not nearly enough. This is Skill 4 in the framework of 9 essential skills. Hybrid memory architectures and knowledge engineering. The solution isn't to abandon RAG, it's to evolve it. We need memory systems inspired by human cognition, combining the breadth of vector search with the depth of structured knowledge graphs. Let's build something smarter. Human memory isn't a single system, it's at least 3. Episodic memory stores what happened to you and when. Semantic memory stores facts and knowledge about the world. Procedural memory stores how to do things, skills, and patterns you've learned. The most sophisticated agent memory architectures mirror this cognitive model. Episodic memory captures the what happened when of AI agent interactions. What did this user ask about last Tuesday? What was the outcome of the project review meeting? What troubleshooting steps were tried before, and did they work? Several companies and their systems specialize in this area, providing time-aware indexing by user, entity, and session. Semantic memory is the agent's knowledge base, the facts and information it knows about the world, company policies, product specifications, domain expertise. This layer requires hybrid approaches, vector embeddings for semantic similarity search, and knowledge graphs for structured queries. You need both. Find documents like this and trace the relationship from A to B to C. Procedural memory stores how-to knowledge, successful problem-solving patterns and workflows. When an agent encounters a familiar problem, it shouldn't reason from scratch. It should retrieve a proven solution pattern and adapt it. This can be implemented as prompt templates, few-shot examples, or cached execution plans. The result is dramatically improved efficiency and consistency. Here's how the 3 tiers work together in practice. An IT support agent receives a ticket about a database connection error. Episodic memory recalls that this specific user had a similar issue 2 weeks ago and what steps were tried. Semantic memory retrieves the current troubleshooting documentation and known issues. Procedural memory provides the proven resolution workflow. The agent synthesizes all 3 to deliver a personalized, informed, efficient response. Vector search is the foundation of modern RAG. The core idea: convert text into high-dimensional numerical representations, embeddings, that capture semantic meaning. Similar concepts end up close together in this vector space, even if they use completely different words. Car and automobile cluster together. Machine learning and AI training cluster together. When you query a vector database, you're asking, find me the documents whose embeddings are closest to my query's embedding. This is approximate nearest neighbor search, and modern algorithms make it blazingly fast, even with millions of documents. Vector databases have made this capability accessible and scalable. Vector search excels at breadth. It finds relevant information even when the exact keywords don't match. It handles unstructured data beautifully: documents, emails, chat logs, meeting transcripts. It answers vibes-based questions. Find me documents similar to this one. Find content about this general topic. This is essential, but it's only half the picture. The limitation: vector search doesn't understand relationships. It can tell you that two documents are semantically similar, but not how they're connected. It can't trace a path from project A to supplier B to risk C. It can't answer questions that require following explicit relationships through your data. For that, you need graphs. Knowledge graphs store information as entities and relationships. Project Apollo is delayed by supply chain issue. Supply chain issue affects budget line item. Budget line item was approved by Sarah. These explicit connections enable something vector search cannot: multi-hop reasoning. Start at one entity, traverse relationships, arrive at insights that would be invisible to similarity search. Graph databases provide powerful query languages for traversing these relationships. You can ask, find all projects 3 hops away from this supplier. Show me everything connected to this risk factor. What's the shortest path from this team to that budget? These are questions that would require dozens of separate vector queries, if they could be answered at all. The graph RAG methodology pioneered the hybrid approach. First, extract entities and relationships from your documents automatically using NLP. Build a knowledge graph. Then use community detection algorithms to cluster related entities and pre-generate summaries. Now you can answer both local questions through graph traversal and global questions through community summaries. Consider financial risk analysis. You need to track complex dependencies between entities, projects, and market events. A supply chain disruption in Asia affects component X, which is critical to product Y, which represents 40% of Division Z's revenue. Graph traversal makes these cascading impacts visible. Vector search alone would never connect these dots. Graphs also excel at temporal reasoning when combined with time-aware indexing. What was the status of Project X on January 15th? How has the risk profile evolved over the past quarter? Who approved what and when? Temporal knowledge graphs, like those built with graffiti, add the dimension of time to your relationship data. The real power emerges when you combine vector and graph retrieval. Vector search casts a wide net, finding semantically relevant documents even with imprecise queries. Graph traversal then digs deep, following relationships to uncover connected information. The combination provides both the breadth to discover and the depth to reason. Contextual embeddings dramatically improve vector retrieval quality. The key insight: when you embed a document chunk, prepend it with context, the document title, section header, or a summary. This ensures the embedding captures meaning in context, not just the isolated words. A paragraph about implementation means very different things in different documents. Context disambiguates. Hierarchical retrieval optimizes for both speed and precision. First, identify the relevant domain or category. Then narrow to specific documents within that domain. Finally, extract the relevant chunks. This check the drawer label before searching the folders approach reduces latency and eliminates irrelevant results from distant domains. When both vector and graph retrieval return results, you need a fusion strategy. Reciprocal rank fusion is a proven technique. Combine rankings from multiple sources, giving credit to items that appear high in multiple lists. More sophisticated approaches use learned ranking models that weight different signals based on query type. The goal is optimal result quality regardless of which retrieval method found the information. For large knowledge bases, community detection is essential. There are algorithms that automatically cluster related entities in your graph, pre-generate summaries for each community. Now, when someone asks a global question, summarize all engineering risks, or what are the main themes in customer feedback, you retrieve and synthesize community summaries instead of processing thousands of individual documents. Let's see this in action with a legal document analysis system. A law firm needs to find precedents and analyze complex case relationships. The hybrid system uses vector search to find semantically similar cases, even when the legal language differs. Graph traversal then maps citation networks, judge histories, and outcome patterns. Temporal indexing tracks how legal interpretations have evolved. The result? 10 times faster case research and discovery of non-obvious precedent relationships. Your implementation checklist. First, design your 3-tier architecture. What belongs in episodic, semantic, and procedural memory for your use case. Second, choose your databases for vectors and for graphs. Third, implement contextual embeddings and hierarchical retrieval. Fourth, build your fusion strategy for combining results. Fifth, add community detection if you're operating at scale. Avoid the common pitfalls. Vector-only thinking that misses relationship reasoning. Poor chunking strategies that lose context. Ignoring temporal aspects of your data. Embedding chunks without surrounding context. Flat retrieval when hierarchical would be faster. Manual graph construction when you should automate entity extraction. These mistakes turn a powerful architecture into an expensive disappointment. Memory is the cognitive foundation that transforms agents from simple question-answering systems into sophisticated knowledge workers. Without proper memory architecture, your agent forgets every conversation, can't trace relationships in your data, and reasons from scratch every single time. With hybrid memory, episodic, semantic, procedural, vector, graph, your agent becomes something far more powerful. It remembers, it connects, it learns. This is skill 4, and it's what separates toys from production systems. All right, that's hybrid memory. Here's what I want you to take away. RAG isn't dead, it's just the starting point. The teams building truly impressive agents aren't choosing between vectors and graphs. They're combining them. They're thinking about memory the way cognitive scientists think about the brain. Episodic for experiences, semantic for knowledge, procedural for skills. My challenge to you, look at your current RAG implementation. Find one question it can't answer well, something that requires connecting information across documents or tracing relationships. That's your signal. That's where hybrid memory pays off. If this was useful, subscribe and stick around and check out future videos in this series. While you're at it, hit that like button and ring that notification bell. That way you will be sure to know when the next video drops. Thanks for watching. Go build something that actually remembers.